What if I told you that Finland built an underground city 450 meters deep in billion-year-old bedrock, designed to protect humanity from the most dangerous materials on Earth for the next 100,000 years? It sounds like science fiction, right? Well, Finland actually completed this engineering miracle, and the result has revolutionized how humanity approaches its most toxic legacy, creating a model that could determine the future of clean energy worldwide. But here's what makes this story truly extraordinary. This project required engineers to design systems that will function longer than human civilization has existed, using principles that challenge everything we know about long-term planning. Picture this. You're descending in an elevator through solid granite bedrock, going deeper underground than most skyscrapers reach into the sky. The elevator ride takes 15 minutes as you plunge 450 meters into the Earth as crust deeper than the Empire State Building is tall. Around you, the rock is 1.9 billion years old, formed when the only life on Earth was primitive bacteria. When the elevator doors open, you enter a vast underground complex that looks like a scene from a science fiction movie. Tunnels stretch for kilometers through solid rock, lit by LED lights that cast eerie shadows on granite walls. The air is controlled by ventilation systems that maintain perfect atmospheric conditions. But despite the high-tech appearance, this facility is designed to operate without any technology at all. This is Onkalo, which means hiding place. In Finnish, the world's first permanent repository for high-level nuclear waste. It represents the most ambitious long-term engineering project in human history, designed to contain the most dangerous materials humanity has ever created for a period longer than recorded civilization. The scale of the timeline is almost incomprehensible. When Onkalo is finally sealed in the 2120s, it will begin a period of isolation that will outlast the rise and fall of entire civilizations. If human history serves as a guide, the languages we speak today will be extinct, our political systems will be unrecognizable, and our technology will be as primitive to future humans as stone tools are to us. Yet the copper canisters buried in Onkalo's deepest chambers are designed to remain intact through all of this change, protecting future generations from radioactive materials that will remain deadly for 100,000 years. The engineering challenge isn't just about building something that works. It's about building something that will continue working when everything else humanity has created has crumbled to dust. But to understand why Finland would attempt such an impossibly long-term project, we need to understand the nuclear waste crisis that threatens every country using atomic energy. Nuclear power provides 20% of global electricity and represents one of humanity's most important tools for fighting climate change. Nuclear plants produce virtually no carbon emissions and can generate massive amounts of clean energy from tiny amounts of fuel. But they also create the most dangerous waste products in human history, radioactive materials that remain lethal for geological timescales. Every nuclear reactor produces spent fuel assemblies containing uranium, plutonium, and dozens of other radioactive elements. These materials emit radiation levels that would kill a human in minutes of direct exposure. The radioactivity decreases over time, but incredibly slowly. It takes 10,000 years for the radiation to drop to levels where brief human exposure might be survivable, and 100,000 years to reach levels comparable to natural uranium ore. The numbers are staggering. Worldwide, nuclear power has generated over 400,000 tons of high-level radioactive waste since the 1950s. This waste is currently stored in temporary facilities, concrete pools, and dry storage casks that require constant maintenance, security, and monitoring. None of these temporary solutions can last more than a few decades before requiring replacement. The temporary storage crisis was becoming desperate. Many nuclear plants were running out of space for spent fuel storage, threatening to shut down clean energy production. Temporary storage sites required massive security operations to prevent terrorism or theft. Most critically, temporary storage placed the burden of protecting deadly materials on every future generation for the next 100,000 years. Finland faced this crisis acutely. The country generates 30% of its electricity from nuclear power and was committed to expanding nuclear energy to meet climate goals. But they couldn't continue generating nuclear waste without a permanent solution that would protect future generations from the consequences of today's energy choices. International experts had studied the nuclear waste problem for decades without finding viable long-term solutions. Some proposed shooting waste into space, but launch failures could scatter radioactive materials across continents. Others suggested deep ocean disposal, but geological activity could return materials to the biosphere. Reprocessing could reduce waste volume, but created new proliferation risks and didn't eliminate the need for permanent disposal. The consensus among nuclear scientists was clear. The only truly safe long-term solution was deep geological disposal. Bury the waste so deep in stable rock formations that it would be isolated from the biosphere even if human civilization completely collapsed. But implementing this concept required solving engineering challenges that had never been attempted. That's when Finnish engineers proposed something that seemed both logical and impossible. They would excavate chambers in billion-year-old bedrock so stable that it had remained unchanged since before complex life existed on Earth. The proposal was controversial from the beginning. Environmental groups worried about creating permanent nuclear contamination that could last longer than human evolution. Geological experts questioned whether any rock formation could be guaranteed stable for 100,000 years. Engineers struggled with designing systems that would function without maintenance across geological timescales. But Finnish scientists had compelling advantages. Finland sits on the Fennoscandian Shield, a geological formation that has remained stable for 1.9 billion years. The bedrock had survived ice ages, continental drift, and massive climate changes without significant alteration. If any geological formation could provide 100,000-year stability, it was the ancient granite beneath Finland. The Onkalo project officially began in 2004, with the most comprehensive geological investigation in engineering history. Scientists drilled hundreds of test holes, studied groundwater flow patterns, analyzed rock chemistry, and modeled geological processes across geological timescales. The investigation took 5 years and cost over $100 million before construction could even begin. The site selection was critical. Onkalo would be built on Olkiluoto Island, which hosts Finland's existing nuclear power plants. The location provided existing nuclear infrastructure, political acceptance of nuclear activities, and geological conditions that had been studied for decades. Most importantly, the bedrock showed no groundwater movement and no geological activity that could compromise long-term isolation. The construction of Onkalo began in 2004 and represented engineering challenges that had never been attempted in human history. Workers had to excavate a spiral tunnel descending 450 meters through solid granite, creating underground chambers that would remain structurally sound for 100,000 years. The excavation itself was a marvel of precision engineering. Giant tunnel boring machines carved through granite harder than concrete, creating a spiral access tunnel 5.5 kilometers long. The descent followed a gentle 10% grade to minimize structural stress and allow vehicle access for construction equipment. Every meter of excavation was mapped and analyzed to ensure the rock remained stable and suitable for long-term waste storage. The underground facility resembles a small city carved from solid rock. The main access tunnel connects to dozens of deposition tunnels extending horizontally from the central shaft. Each deposition tunnel is 350 meters long and will contain deposition holes drilled 8 meters deep into the tunnel floor. The entire complex covers an area equivalent to several city blocks, all excavated from solid granite. But the real engineering challenge wasn't excavation. It was designing disposal systems that would function without any human intervention for 100,000 years. Traditional engineering relies on maintenance, replacement, and active monitoring. Onkalo had to use passive safety. Protective systems that would continue working even if human civilization completely disappeared. The disposal concept is elegantly simple. Spent nuclear fuel assemblies are placed inside copper canisters designed to last 100,000 years. The copper is so pure and thick that it will resist corrosion even in underground conditions. Each canister is surrounded by bentonite clay that swells when wet, creating an impermeable barrier around the waste package. The multiple barrier system provides redundant protection. If groundwater somehow reached the waste, it would first have to penetrate the stable granite bedrock that has remained unchanged for nearly 2 billion years. Next, it would encounter the bentonite clay buffer that expands to seal any cracks or gaps. Finally, it would need to corrode through copper canisters designed to resist chemical attack for geological timescales. Testing each component required unprecedented research. Scientists exposed copper samples to simulated underground conditions for decades to verify corrosion resistance. Bentonite clay was tested under extreme pressure and temperature to ensure it would maintain its sealing properties. Rock mechanics experts analyzed granite behavior under stress conditions that would persist for millennia. The copper canisters themselves represent a masterpiece of materials engineering. Each canister weighs 25 tons and consists of a cast iron insert surrounded by 5 centimeters of pure copper. The iron provides structural strength, while the copper provides corrosion resistance. Manufacturing techniques ensure that the copper shell has no defects that could compromise long-term integrity. Quality control standards exceed anything used in conventional engineering. Every canister undergoes non-destructive testing using ultrasound, X-rays, and other techniques to verify structural integrity. The manufacturing process is designed to eliminate any possibility of defects that could compromise 100,000-year performance. The deposition process is equally carefully designed. Each copper canister is lowered into a deposition hole drilled precisely into the tunnel floor. The canister is surrounded by bentonite clay pellets that are compacted around the waste package. The deposition hole is then sealed with more bentonite, and eventually, the entire tunnel will be backfilled with clay. The engineering required workers to think across timescales that challenge human comprehension. Every material, every design decision, every construction technique had to consider performance over 100,000 years. Normal engineering standards apply to structures lasting decades or centuries. Onkalo engineering had to account for climate changes, ice ages, and geological processes that operate on timescales beyond human experience. Perhaps most remarkably, the facility was designed to be completely forgotten. Unlike monuments or structures intended to last, Onkalo's success depends on future generations never discovering it. The repository will be marked only with simple warnings in multiple languages, but these markers are expected to become meaningless as languages evolve and civilizations change. The construction workforce faced unique psychological challenges. They were building something designed to outlast everything they had ever known. Workers routinely described the surreal experience of creating structures intended to function long after their own civilization had become ancient history. By 2015, the main excavation was complete, and testing of disposal systems began. Full-scale experiments verified that copper canisters could be manufactured to specification, that bentonite clay performed as predicted, and that the granite bedrock remained stable under the stresses of excavation and operation. International scientific oversight ensured that every aspect of the project met the highest safety standards. Regulatory approval required demonstrating safety over 100,000 years using computational models, laboratory experiments, and natural analogues of long-term waste isolation. The first radioactive waste arrived at Onkalo in 2023, marking the beginning of operations for humanity's first permanent nuclear waste repository. The facility will operate for about 100 years, gradually filling with copper canisters containing spent nuclear fuel from Finnish reactors. But the most critical phase will begin around 2120, when Onkalo is finally sealed forever. The access tunnel will be backfilled with clay and rock, creating a barrier designed to discourage future excavation. After sealing, the repository will begin its 100,000-year mission of passive protection without any human intervention. The psychological impact of completing Onkalo has been profound for the global nuclear industry. For the first time since nuclear power began, there is a demonstrated solution for the permanent disposal of high-level radioactive waste. The technical feasibility of deep geological disposal has been proven, and the regulatory pathway has been established. International delegations regularly visit Onkalo to study techniques that could be applied in their own countries. The Finnish approach has become the global standard for nuclear waste management, with over 15 countries developing similar deep geological repositories based on Onkalo principles. The global impact of Onkalo's success has been transformative for the future of nuclear energy worldwide. What began as Finland's solution to a national nuclear waste problem has become humanity's template for managing radioactive materials across geological timescales. Sweden immediately launched construction of a nearly identical facility at Forsmark, using Finnish technology and experience. The Swedish repository will handle waste from their nuclear fleet using the same copper canister and bentonite clay approach proven at Onkalo. Construction began in 2023, with operations planned for the early 2030s. Canada adapted Onkalo principles for their deep geological repository in Ontario, designed to handle not just reactor waste but also radioactive materials from nuclear weapons programs and medical isotope production. The Canadian approach uses the same multiple barrier concept, but adapted for different geological conditions and waste types. The United Kingdom announced plans for a deep geological repository based on Onkalo engineering, ending decades of failed attempts to find permanent solutions for British nuclear waste. The success of the Finnish approach finally provided the technical confidence needed to proceed with permanent disposal rather than continued temporary storage. Most remarkably, the United States, which had failed spectacularly with the Yucca Mountain repository, began reconsidering deep geological disposal using Finnish methods. American nuclear engineers studied Onkalo extensively, analyzing how the proven approach could be adapted for US geological conditions and regulatory requirements. France, despite their extensive nuclear reprocessing programs, acknowledged that some radioactive materials require geological disposal and began investigating deep repository options based on Onkalo technology. The French approach would handle vitrified high-level waste from reprocessing using similar copper canister and clay buffer systems. Even countries with smaller nuclear programs recognized Onkalo's importance. Switzerland, Belgium, and South Korea began collaborative projects to develop regional repositories using Finnish expertise and proven technology. The economies of scale made geological disposal feasible even for countries with limited nuclear waste inventories. The success created a positive feedback loop for nuclear energy development. Countries that had delayed nuclear power expansion due to waste concerns began reconsidering atomic energy as a climate solution. The existence of proven permanent disposal technology removed one of the major obstacles to nuclear power growth. International nuclear industry organizations promoted Onkalo as evidence that nuclear waste could be managed safely and permanently. The facility became a powerful tool for addressing public concerns about radioactive waste, demonstrating that technological solutions existed for even the most challenging aspects of nuclear energy. But perhaps most importantly, Onkalo's success changed how humanity thinks about long-term responsibility and intergenerational justice. The project demonstrated that current generations could take permanent responsibility for their technological choices rather than passing dangerous legacies to future generations. The engineering innovations developed for Onkalo found applications beyond nuclear waste management. The techniques for designing systems to function across geological timescales proved relevant for carbon dioxide storage, hazardous chemical disposal, and other long-term environmental challenges. Research collaboration expanded globally as universities established programs in deep geological engineering and long-term materials science. Students from around the world traveled to Finland to study techniques that would be essential for managing technological legacies across geological time. The psychological and philosophical impact extended beyond engineering. Onkalo forced societies to confront questions about responsibility to future generations, the permanence of technological choices, and humanity's role as stewards of geological processes. The project became a case study in how present decisions affect distant futures. Environmental organizations that had opposed nuclear power began acknowledging that Onkalo provided genuinely permanent solutions to radioactive waste concerns. While many remained critical of nuclear energy, few could argue that deep geological disposal wasn't a major improvement over indefinite temporary storage. The success also influenced international nuclear proliferation policy. Countries developing nuclear weapons faced pressure to demonstrate similar responsibility for radioactive waste management. The existence of proven disposal technology made it harder to justify accumulating radioactive materials without permanent disposal plans. Economic analysis revealed that geological disposal, while expensive up front, provided enormous long-term savings compared to indefinite temporary storage. The costs of maintaining security, monitoring, and replacing temporary storage facilities for 100,000 years far exceeded the expense of permanent geological disposal. Most remarkably, public acceptance of nuclear energy increased in countries that committed to implementing Onkalo-style repositories. Polling showed that the existence of permanent disposal solutions significantly reduced public concerns about nuclear waste and increased support for nuclear power as a climate solution. The scientific research spawned by Onkalo advanced understanding of geological processes, materials science, and long-term engineering in ways that benefited multiple fields. Studies of 100,000-year copper corrosion provided insights relevant for archaeological conservation, infrastructure design, and materials research. International cooperation on geological disposal became a model for addressing other global challenges requiring long-term coordination. The technical success and regulatory acceptance achieved in Finland provided frameworks for international collaboration on climate change, biodiversity conservation, and sustainable development. Today, Onkalo operates as a testament to human capability for long-term thinking and engineering excellence. The facility receives spent nuclear fuel from Finnish reactors and processes it for permanent disposal, using techniques proven over 2 decades of development and testing. Visitors to the underground complex encounter technology designed to outlast human civilization. The control room monitoring systems track every aspect of operations, but they also serve as reminders of temporary human oversight. In about 100 years, when Onkalo is sealed forever, all of this technology will be removed, leaving only passive barriers that require no human intervention to maintain their protective function. Research continues on improving disposal techniques, extending canister lifetimes, and enhancing barrier performance. But the fundamental challenge has been solved. Humanity now possesses proven technology for permanent disposal of high-level radioactive waste. The underground chambers that once seemed like science fiction have become humanity's gift to the distant future. Protection from the most dangerous materials our civilization has created, guaranteed to function longer than recorded history. From nuclear waste crisis to permanent solution, from impossible engineering to proven technology, from national project to global model, Onkalo demonstrates that humanity can solve problems across geological timescales when engineering excellence meets long-term commitment. The 100,000-year project that began in Finnish bedrock has become a template for protecting future generations from the consequences of today's technological choices. What other long-term challenges do you think humanity should address with similar geological scale thinking?